In this lecture, I'm going to talk about trig integrals. We know a little bit about trig integrals already, right? We know things like the integral of sine, right? Integral of sine, negative cosine of x plus c. We know the integral of cosine of x is sine of x. All right, so we know a few things. We know the other ones as well. We also know, something like sine of 2x, right? So remember, with this is basically the chain rule in reverse. And when we're undoing the chain rule, we can think of this as u substitution. So we could let u equal 2x so that du equals 2 dx. So I've kind of substituted here. I want to do sine of u. So what I have left to replace is a dx. So we divide by 2 and 1/2 du equals dx. So we replace this with 1/2 du. The 1/2 comes out, right? And we just end up with 1/2. Well, no, antiderivative, right? So negative cosine. We already know that from up here. Antiderivative of sine is negative cosine. And then we put our u back in plus c. All right. So likewise, if I wanted to take the antiderivative of cosine of 2x, we could go through this same process, and we would end up with 1/2 sine of 2x plus c. Really, if you just think about the fact that when I take the derivative of this, I multiply by what's in here. Then taking the antiderivative, I would divide by what's in there. So that when I took the derivative of this thing, I should get back to cosine 2x. And in fact, it doesn't really matter that it's a 2, right? Does it make sense that it doesn't matter that this whole process here? So for example, if I wanted to take the antiderivative of sine of n times x, where n is just any number, it doesn't even have to be an integer, but it usually is, then I could let u equal nx, du equals n dx, so that 1/n du equals dx. We go through that whole thing again, we have a 1/n out front, we're taking the antiderivative of sine of u, du, we end up with 1/n, actually negative, right? Cosine nx plus c. This will be useful for us later on to not have to go through this substitution every time. So, and then likewise we have cosine of nx dx would just be the antiderivative, 1/n sine nx plus c. All right, so those are a couple of things we already know how to do. One more thing that we know how to do is something of the form, if we had sine squared of x times cosine of x dx. So remember, this means that you're taking sine of x and then you're squaring it, all right? So you might recall that the way that we handled this was to do a substitution. So if we let u equal sine of x, then du equals cosine of x dx. So this piece is covered by du, and then the sine becomes u, and we're squaring it, so our new integral now is u squared du. That's easy to handle, right? So we would end up with 1/3 u cubed plus c, changing everything back to what we started with. We end up with 1/3 sine cubed of x plus c. All right? And likewise, if we had cosine squared and sine was to the first power, we could do a similar substitution. So this is by way of review, but also it's to help motivate what we're doing here in 7.3 with these trig integrals, because if we have something, maybe I'll start with a different color now, because we're getting to kind of the new stuff. What if I had something like just sine squared? All right. Notice this substitution no longer works because when I take the derivative, I have this factor of cosine that's not here, right? So substitution won't work. And if we go back to the things that we did before, having something like sine of 2x or sine of 3x or 5x or whatever it is not the same as squaring sine. So we don't really have a way to handle that. Likewise, if we had something like sine squared x times cosine squared x dx. So again, we could do a substitution of u equals sine, and then du would be cosine x dx. So this would be u squared, but notice this isn't quite that, right? And there's not really a way, we can't just throw another cosine in there to make it work. So we don't really know how to handle things like this. What was unique up here is that one of them was to the first power. So when we did the substitution, we just got out the derivative of that and we were able to replace it with du. But when it's not to the first power, when both of them are raised to a power, or if there's not another one in there, this u substitution won't work out. And so we need some other ways to handle these types of integrals. So there's a couple of identities that we're going to use in this section. One is called the Pythagorean identity. You should already know it, but here it is again. It is sine squared of x plus cosine squared of x equals 1. All right, and you can kind of think of this as coming from the unit circle. So in the unit circle, all right, it's right on the x and y axis. If I draw any triangle, then I can think of this side, the x side, as cosine. Here's x, so that's cosine x, and then the height of this thing is sine of x. But we know, since this is a right triangle with a radius of 1, the Pythagorean theorem tells us that this side squared plus this side squared equals that side squared. Well, we already know that side's 1, right? So this just comes right from the Pythagorean theorem. Another one is that sine squared of x equals 1/2 1 minus cosine of 2x. So I'm not going to derive that one. If you're in Calc 2, you've seen this in a pre-calc or a trig class at some point. So that's just a reminder. And then the third one is we'd like to get an expression for cosine squared of x. All right. Well, from up here, we see that, so one expression would be that cosine squared of x is just 1 minus sine squared of x, right? So, and then likewise, we could also say that sine squared is 1 minus cosine. We'll see why, or cosine squared, I should say. So we'll see why sometimes this might be useful, but sometimes this might be useful. So for example, if I let this equal 1 minus sine squared of x, well, here's an expression for sine squared of x, all right? So that gives us 1 minus 1/2 times 1 minus cosine 2x. If we distribute that 1/2, we end up with minus 1/2, and then that's minus a negative, so plus 1/2 cosine 2x. All right, simplify a little bit. We have the 1 minus 1/2, which is 1/2 plus 1/2 cosine 2x. Simplify one step further, we can factor a 1/2 out of there. We end up with 1/2 times 1 plus cosine of 2x. So notice the similarity between this and this. So for sine squared, it's 1/2 1 minus, and for cosine squared, it's 1/2 1 plus cosine of 2x. Cosine of 2x in both cases. Okay, so let's actually use this one right here and see how this might help us with this one up here. I'm going to use yet another color because the blue is getting tired. All right, so what we're looking at is this sine squared. So take the integral of sine squared of x dx, and we're going to do this substitution right here. So instead of that, I'm going to rewrite this as 1/2 1 minus cosine of 2x dx. All right, now this constant can come out front, so that's the first thing, and we're just left with 1 minus cosine 2x dx, that whole thing. Well, we already know how to do this, right? So here's where the substitution is helping us already. So I've got this 1/2 out front, that becomes x, and we've already done this one today, so that's minus sine, minus 1/2, right? Sine of 2x plus c. All right, you could distribute the 1/2 if you wanted to, but this is fun. So I also want to point out here how this was useful, but another way I could have written this is 1 minus cosine squared dx. All right, and then that just comes from here, right? If sine squared plus cosine squared equals 1, then we already have it down here, but likewise sine squared of x equals 1 minus cosine squared of x. All right, but notice this doesn't really help us, because now instead of taking the antiderivative of sine squared, now we have to find the antiderivative of cosine squared, which we don't know any better, at least not without this type of a substitution. So this is where these types of substitutions using the identities, they take a little bit of practice. You have to figure out what would be a useful substitution and what might not be so useful. And really that just comes with some practice. Let me give you one more example then. Basically the example that we started with, right? So we looked at this one, and here's another case that we didn't really know how to handle. All right, the U substitution didn't work. So let's think about how we might do that one. All right. Okay, so let's rewrite it first. Again, I'll just use a different color just to kind of separate this example. So what we are looking at was the antiderivative of sine squared times cosine squared of x dx. So here's a place where this might be. I'll tell you now, there's a lot of different ways you can approach this. And so one is going this route. So let's just see what happens if we go this route. If we put in 1 minus cosine squared of x, and then times cosine squared of x, and we can distribute. So now we have cosine squared of x minus cosine to the 4th of x dx. All right, and we know how to handle the cosine squared, right? I mean, basically we could do it just like this, but instead of using this identity for sine squared, we could use this one right here for cosine squared. But we also have a cosine to the 4th. So let's come back to this one and think about another way that we could approach this. Well, we have this identity here for sine squared, and then we have this one down here for cosine squared. So let's try plugging both of those in and see what we end up with. All right, so just to kind of leave this up here so you see where things are coming from. So yet another color, might as well use them all. So we're going to kind of maybe come back to this, but let's go over this way, and instead we'll put in, so we'd have 1/2, so for sine squared, 1 minus cosine of 2x, and then over here we've got another 1/2, 1 plus cosine of 2x. All right, yeah, I guess there's another parentheses there, and then that's our new integral. So first we have this 1/2 times 1/2, and that's a 1/4 that can come out front. All right, so now I got 1 minus cosine 2x times 1 plus cosine 2x. Now, at this point, I know a lot of people would like to integrate these separately and then multiply after they integrate. But if we could do that, we wouldn't need integration by parts. We don't need this anymore. So let me see. It might be hard to see. Let's try to fix that. All this Portland sunshine. All right, that's better. Okay, but so we can't. The integral of a product is not the product of the integrals. All right, so that's why we have integration by parts. And some of you are probably having an allergic reaction to hearing the word integration by parts. So let me just put you at ease now so we know we're not going to do integration by parts here. But we can expand this out. So let's go ahead and expand this out and see what we end up with, see if it's something that we can handle. All right, so I have 1 times 1, that's 1. Now notice these are exactly the same except for a plus and minus. So that means when I FOIL this out, the outer and the inner are exactly the same except for the opposite sign. So I have a cosine 2x and a minus cosine 2x. Those will cancel. And then I have this, I have cosine 2x or minus cosine 2x times plus cosine 2x. That's minus cosine squared of 2x. So this certainly looks simpler, right? Now we still have this cosine squared, but at least we don't have 2 of them, right? We got rid of the sine squared, and we're down to a cosine squared. So let's think about how we can use. Now we've already used it once, right? We said this was the same thing as cosine squared of x. Notice that if I start off with x, I end up with 2x. So what do you think I'll end up with if I start off with 2x? I mean, so I'm basically kind of, here's where another color might be helpful. So this is kind of my input here. So if I put in 2x for x, then that means I need to put in 2x for x here, right? So what that's going to give me, of course, is a cosine 4x. So I've got 1/4 out front, 1 minus, and this is where I'm going to make my substitution. It's going to be the substitution that looks like this, except I'm going to now have a 4x for the reason that I just stated. So it's going to be minus 1/2, 1 minus, sorry, that's a plus, right, for cosine, plus cosine 4x dx. Okay, so we can maybe separate these out. I've got a 1/4, I'm going to bring it back here, 1/4, just the integral of 1 dx, minus, I'm going to bring the 1/2 out front, integral of 1 plus cosine of 4x dx. And remember the 1/4 is times the whole thing. All right, that's easy. So that just gives us an x. All right, and I have minus 1/2, and this is going to give me an x. And here I end up with plus 1/4 sine of 4x. And I'm not going to go through that substitution. We talked about that at the beginning. It doesn't matter what number is here. I'm going to divide by it when I take the antiderivative, right? Okay, and then I have a plus c. Now, feel free to distribute, but I'm out of room and also out of time. So I'm going to stop there and just kind of look at what we did here. So we did both of those substitutions. Expanded, here's the little trick here. I have a cosine squared 2x, so I need to put in 2x for x in my identity, so I end up with 4x. The rest of it's pretty straightforward. I will come back to this one right here, just to kind of see how that would go. And here's the, I won't do the whole thing out, but I'll just give you I'll give you a hint and let you work it out for yourself. So I can think of this as cosine squared of x squared. All right. So I've got this cosine squared. I already know what that identity is, right? We said that that's the 1/2 1 plus cosine 2x. All right. Well, we can, if we rewrite this, and this cosine to the fourth is cosine squared squared, we can use the same identity right here, but we're going to have to square that out before we do the antiderivative. So try that. You should end up with something equivalent to this, but it doesn't mean it'll look exactly like this. Because of these substitutions, you might at the end you might have to substitute back if you want things to look the same. But go ahead and try this as an exercise. Okay, so that's the introduction to trig integrals.